So I'm adding to this a little extra stuff. I'm adding um, a one page of notes on fluid friction, and specifically the friction that an airplane or a car encounters as it speeds down the highway or is flying through the air. So at low speeds, as I mentioned before, um, you have the laminar airflow, and the friction from air resistance is proportional to the velocity. So that means linear scaling. That means that if you're going, let's say, 10 meters per second, you would have, well, 10 is too fast. Let's say 1 meter per second, you would have a certain amount of friction. If you went 2 meters per second, oh, now you're going to have twice as much friction. 3 meters per second, 3 times as much friction. But there comes a point, maybe around 10 meters per second, where you start to get turbulence, and you may get a certain amount of friction at 10 meters per second, but now let's say you go 20 meters per second. Ooh, well, you've doubled it. Now you've got double squared, 4 times as much friction. Let's say you go 3 times as fast. Okay, now you're going to have 9 times as much friction. So that's what the turbulence does. Now, let's say you want to actually figure out, here's a car, what's the air friction going to be? Here's the formula you need to use. So we have, the formula is 1/2 times a number called C, which is called the drag coefficient, which had to be measured by engineers using wind tunnels and so on. And they've done lots of measurements for many different shapes. Here's a few of them. So for example, if you have a spherical car, not very realistic, but it would have a drag coefficient of 0.47. More realistic would be this bottom one here. This shape has a drag coefficient of 0.09, which is a lot less than 0.47. So having a streamlined car helps a lot to cut down on air friction. It's going to depend on the density of air, and which is at sea level is 1.3 kilograms per cubic meter. It's going to depend on the frontal area, this capital A, the frontal area. And so to figure that out, you need to look at your car from the front, like the car is heading towards you, and figure out from that perspective, what is the area of the front grille, the windshield, and so on. And so just looking at it from the front. And then here's the velocity, which gets squared. I mean, we're talking about cars, so they go pretty fast. And so there you go. That's the process. And here's a little example. I've got a pool ball, so we're going to use the sphere, and it's falling at 5 meters per second. What's the air resistance going to be? I figure out the frontal area of the pool ball. It's pi r squared, which you plug in and you get 0.00126 meters squared. And so I have 1/2 times the 0.47 from the sphere times the density of air, 1.3, times the frontal area times the velocity squared, and I get my answer. The air friction on the pool ball at this speed would be 0.0096 newtons. Okay, so this is really practical stuff, and so I think it's worth explaining to you. I hope you find it useful too. All right, that's it for the first part of the notes on friction. Thank you.